I'm going to show you two development of membrane on a computing medium. The first one where membranes are just isolated from each other, and the second one they form a 2D grid, so it's a 2D grid which develops. Before showing those developments, I'm going to illustrate a very important building block, which is homogeneization. Homogeneization of particles, homogeneization of membranes, a hierarchy of membranes, and homogeneization of also membranes linked together by channels. We are going to show some basic functioning of the general purpose cellular automata, namely how to homogeneize particle using repulsion and distance field. So we have here 24 particles, and the rule, which is only 3000 gates per square, is homogenizing, as you can see. How does it work? It uses distance field. One distance field from the kernel towards the ring inside, around it, 2, 4, 6, and another one from the ring towards the particle. As you can see, the distance is encoded modulo 8 using only 3 bits, so it's finite states. The grid could be much larger, like billions of cells. We still use only 3 bits, because what we really use is level, the difference between distance of adjacent cells. And how does homogenization work? Well, it just move particle away from the ring and move ring away from particle. The algorithm works for more cells. It also works for hierarchy. You can see that the hierarchy is being homogenized. The distance field that was going from the particle to the ring is also going from the outer kernel towards the skin. As you can see, here, 2, 4, 6, 2, 4, 6, and the same for the other distance. The one going from here to here is also going from here to here. So there is 2 distance, one from the skin to downwards to the atoms, and another one, so that we can place the blue matter in between the two. We can also homogenize particles with channels. The channels, the green region remains adjacent to the blue particle as the thing gets homogenized. And so finally we are moving pairs of values. This can support values. So we have hardware free pairs. can think of it also as molecules if you'd like. Okay, it works with more channels. You can see though that there is a problem here because those should become near each other and they do not. Repulsion is used all the time. In fact, long distance forces are mainly repulsion. So for example, when we want to do division, first we install this green matter, and when the particle divide, it makes a hole in the green matter, and the green matter goes away from the particle. While remaining connects, so it cannot go away here because there is something which binds it. And the red goes away from the green. Okay, that goes. So that the green becomes a median of the two and defines a cutting plane. So that when the membrane is sucked in, the whole thing is sliced in two. We now present a general purpose cellular automaton. So when I run it, instructions come from the host from the four corners. Here it's a sequence of 3 instructions that you also see here. The first instruction selects the blob B. So the selected flag becomes on just after the instruction. Then the next instruction sets the region where selected is true. And then the third instruction, D, trigger a division. So when it triggers a division, the whole region becomes an independent thread of computation from the rest, which means signals which will subsequently be emitted within the region will not cross the boundary of the region. Those signals carry a micro instruction. We need 4 micro instructions to perform division. So the first micro instruction is emitted right when the particle in the center is in the center. It divides and it creates a hole in the green material, which is a wall. This hole then extends. The second microsignal is sent by each blue kernel after the division, and on this example you can see it is not sent at the same time. The left blue kernel sends it much earlier than the second one because in order to be sent, the blue kernel needs to be in the middle. It creates strangling of the membrane along the median until there is only one single cell which maintains the connection. We'll reach this specific configuration with there is a final cut can be performed and the two cells separate and the signal
the last signal, which says that division is finished, is sound, and you see now it goes from blue to back to green, what was before. That specifies that this is no more an independent thread of computation. So the next instruction which are waiting here, you can see them, are going to penetrate right after. Okay, this is another division,
but this time
we have two distinct regions. Okay, B. So the two regions are going to perform division independently, one from the other one. The same sequence of signal are going to bounce within those two regions, and the same steps are performed, leading to 4 cells. And once again, the third instruction for division penetrate, and so it's gonna trigger 4 division. Okay. And it's going further, faster and faster, because time is proportional to the diameter, which is divided by square root of 2 each time. And the division perform in a pipeline way. Okay. So this signal has already triggered division here, but not yet here, and it's triggering division and goes forward here. So very quickly, in fact, in a time proportional to the whole diameter, we can generate using 1, 2, 3, 4, 5, 6, 7, 8, 9
division instruction 512 cells in no more than 700 iterations.
This is an exponential development. I'm going to show you now sequential development.
When a cell divides, there is 2 offspring, one negative and one positive, and we'll select only the positive for further division. So only one of the 2 offspring gets divided, so we have 3 and then 4 cells, because it's always only one that gets cells that gets divided.
Showing you this slower development, so that you can clearly see that as development goes on, repulsion also goes on between particles, and they get replaced automatically, so that development can happen.
Here I show again the exponential division, so that you can see how fast it goes from the beginning to the end. In only 700 iterations, it generates 512 cells. We will now present a more difficult development. We develop a 2D grid of membrane using 14,000 gates. The ancestor cell has now 4 channels here in blue.
And those channels have identifier, N for north, you can see at the extremity of the channel, W for west, E for east, S for south. So using this idea, we're going to be able to select the channel, which is done by the first extraction, which select north and also horizontal, but it is not yet north and south. So the north and south are now independent region, which are going to be divided. This is a region here. So going to be divided, those region. We find the middle using the same median as before, and once the middle is found, it's cut. So the north and south channel are cut. They get distinct polarity. Okay, this is polarity minus, this is polarity plus. Therefore, when the instruction for division comes, the fact that there is different polarity here will be used to determine cutting plane.
The median becomes thin, and we identify when it's a nice thin median, and then send the first micro instruction.
Then the next signal after this is launched when the particle divides, and we make sure that one copy is generated on each side of the median. And after division, the same thing, the same program is used, so there is no more logic gate to add. We will use the same logic gate to finish the division. Okay, the same division we use for exponential development that I already show you, the division of a ring without channel. But the channel are here, so because we are careful to separate the plus and the minus, the left get the minus, the negative channel, on the right the positive channel. And so the division finished, and the next step will be to divide those three channels, the east and the west, on a newly created channel. This channel was created upon division, right when division was performed. Here, bloom, we have a new channel being born. Okay, so those three. This one is identifier V. So those three channels will get divided by, because we select V and east and west. So that those three gets divided now, and the same thing happens, but this time the cutting plane will be here. Okay, there are two independent zones. Okay. Those two zones are independent. And as for the exponential development, the rest go faster and faster because time is proportional to the diameter of the cells. So now we are going to have a cut in this plane. It's a bit messy, as you can see. It's not really straight. This is ongoing work. We've not yet reached the right framework to do that. So I show another step of development, and I'll stop and show you the grid. Okay, it's finished. So you don't see very well the grid, so to see it,
Blue channels defines lines, and green channel defines columns.